Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Aqil Asyraaf bin Muhammad Mahdi. Today I'm going to present about Chitosan oil palm trunk powder modified in 1-butyl 3-methyl-imidazolium acetate for the adsorption of Malachite green. I will cover the introduction, literature review, methodology, results, and finally the conclusion and some recommendations. Firstly, this study revolves around the removal of dye in wastewater using low-cost materials such as chitosan. However, chitosan has limitations such as low stability and low adsorption capacity. To solve this, we can incorporate chitosan to a solid adsorbent to make composite and employ new solvent systems such as ionic liquid plus acetic acid to improve chitosan solubility. This study is important to help restore safe and clean water, which aligns with SDG number 6, clean water and sanitation. Malachite green is a water-soluble cationic organic dye. It can cause various harm to the eye, respiratory system, nervous system, heart rate, liver, and brain if digested. Chitosan can be modified as its amino and hydroxyl groups, but unstable in acidic condition. For OPT, its structure consists of lignin, hemicellulose, and cellulose. In employing new solvent systems, ionic liquid was chosen because of its low volatility, improved selectivity, and tunable. Combined with acetic acids, chitosan dissolution can be improved. This study used PFO and PSO kinetic model and Langmuir and Freundlich isotope model for data fitting. CSOPT was prepared using chitosan, OPT, 1-butyl 3-methyl-imidazolium acetate, acetic acid, and distilled water. After treatment with alkali, rinse with distilled water and dried at 80 degrees Celsius, CSOPT adsorbent was obtained. The adsorbent was characterized using FTIR and SEM-EDS. Proceeding to batch adsorption to study the effect of pH, adsorbent dosage, initial concentration, and contact time. Adsorption, kinetics, and isotope was studied using PFO and PSO kinetic model, and Langmuir and Freundlich isotope model. Lastly, adsorption dissolution study using distilled water and hydrochloric acid. For chitosan spectra, there are hydroxyl, amino, and pyranoside ring group appeared. For the OPT spectra, there is hydroxyl group that appeared near wave number 3000 and a sharp peak around wave number 1700, largely originating from hemicellulose and lignin. Other peaks are aromatic C-double-bond-C for lignin, CH bending in cellulose, and pyranoside ring groups. In CSOPT before and after adsorption, the peak at wave number 1700 from OPT disappears because of the large amount of lignin and hemicellulose removed. The bands corresponding to hydroxyl and amino experience a slight shift to lower frequencies, indicating a disruption in hydrogen bonding network of chitosan between acetic acid, imidazolium ionic liquid, and chitosan chain. This shift was attributed to the reconfiguration of a new hydrogen bonding network of chitosan. After the adsorption of Malachite green, a new peak appeared at wave number 1500, which indicates that there was an increase of nitrogen in the compound. Additionally, the intensity of hydroxyl and amino peak increased slightly, corresponding to the increased number of nitrogen in the compound. The surface of the untreated OPT is tight and uneven due to the existence of lignin and hemicellulose holding the fiber of OPT. After modification with chitosan solution, a streamlined surface and less dirt are shown on the surface of the CSOPT. After the adsorption of Malachite green, the surface changed into a more uneven structure, which indicates that Mg was attached to the surface of CSOPT. The EDS element table shows a dominant elements of carbon, oxygen, and silica. For the untreated OPT, there were still traces of potassium, magnesium, and calcium. After the modification of chitosan with the chitosan solution, all trace of potassium, magnesium, and calcium was gone, and a new nitrogen peak observed indicates that chitosan is successfully attached to the OPT surface. After the adsorption of Mg, the amount of N increased, and there was a new sighting of chlorine peaks, which indicates that Mg successfully attached to CSOPT. The value of pH at 0 point charge is 5. At the pH at 0 point charge, the concentration of positive and negative charge on the surface is equal, resulting in a net neutral charge. If the pH of solution is higher than pH at 0 point charge, the surface of the adsorbent has more negative charge, which will facilitate the adsorption of cationic dye. On the other hand, if the pH of solution is lower than the pH at 0 point charge, the surface of the adsorbent has more positive charge, which will facilitate the adsorption of an ionic dye. pH of the solution plays a crucial role in the adsorption process, impacting both the surface characteristic of the adsorbent, influences protonation, electrostatic attraction, and repulsion in the solution. The absorption of Mg at pH 8 on the CSOPT is higher than of the untreated OPT, indicating that the modification to increase the absorption of Mg on CSOPT is a success. The highest dye uptake rate occurs at pH 8, where chitosan's positive charge decreases due to excess hydroxide ion, leading to strong absorbent-absorbent interaction due to opposite charges. This is attributed to the pH at 0 point charge at CSOPT at 5, leading to increased hydroxyl ion concentration above the pH at 0 point charge, enhancing electrostatic attraction between the cationic Mg and the negatively charged sites on the CSOPT. The efficacy of removing pollutants from aqueous solution is significantly influenced by the quantity of the absorbent used. Increasing a CSOPT dosage led to an elevation in Mg absorption removal. However, this rise in absorption removal coincides with the decrease in the absorption capacity of Mg dye. The increased absorption removal is attributed to an increase in accessible active sites for Mg absorption. Conversely, the decrease in absorption capacity with increasing absorbent dosage is linked to a greater availability of unsaturated sites for the dye absorption. Further increasing the absorbent dosage to 0.1 resulted in a slight reduction in absorbent removal, potentially due to overlying or aggregation of active sites, and a decrease in overall available absorbent surface area. The absorption of Mg dye on CSOPT absorbent was studied at room temperature by varying contact time and initial concentration. Within the first 20 minutes, cationic Mg molecule quickly attached to the outer surface of the absorbent. However, the rate of absorption gradually decreased as the Mg molecule encountered resistance during mass transfer, penetrating deeper into absorbent pores and achieving equilibrium at 20 minutes. After 20 minutes, there are no significant change at lower concentrations. Initially, a higher number of binding sites were available, but over time, these sites became saturated with Mg molecules, resulting in a reduced absorption rate. Equilibrium was attained when saturation occurs, leading to a plateau in the absorption graph and signaling the conclusion of the absorption process. At higher initial program, increase the driving force to overcome the mass transfer barrier, resulting in a longer time to reach equilibrium. The amount of Mg absorbed increased over time, and at higher concentration, equilibrium was reached after a longer duration, highlighting the dependency of absorption on the initial concentration of the solution. The study utilized both PFO and PSO model. While both models in the study resulted in R-square of 1, indicating a perfect fit, differences in chi-square and RSS value favored the PSO model, indicating a better fit than PFO. The absorption capacity of CSOPT increased as the dye concentration increased, because stronger driving force required to overcome the absorbent liquid mass transfer barrier. It is assumed that the rate-limiting step for this absorption is the chemabsorption process involving the sharing or exchange of electrons between adsorbate and adsorbent. The manifestation of step-like isotherm, particularly when organic compounds are adsorbed, arise from cooperation and interaction among the adsorbed molecule. Multilayer stepwise isotherm, categorized as Type 6 isotherm, have more than one inflection point and local maximum, presumably due to the non-monolayer nature of adsorption. The isotherm shape suggests a potential change in adsorption interaction, possibly related to the formation of multilayer of dye molecule. The three-step multilayer stepwise isotherm delineates distinct stage of adsorption and can be viewed as three-stack isotherm, with the first stage adsorption sites saturating at lower concentration than the second and third stage. The extended plateau implies complete saturation of dye molecule on active sites, presenting a barrier to forming additional layers. CSOPT shows a high absorption capacity of 1000 mg/g. Distilled water presents a low desorption value compared to hydrochloric acid. The results show that not all dye was recovered, probably due to electrostatic attraction or other stronger interactions such as hydrogen bonding and pi bonding between the adsorbents and the Mg dye molecule. In conclusion, CSOPT material is characterized by its surface properties and successful chitosan coating, confirmed by SEM and EDS analysis. Batch absorption studies reveal that the optimal conditions for maximum Mg absorption are at pH 8, a contact time of 20 minutes, and CSOPT adsorbent dosage of 0.02 gram. Adsorption kinetics and isotherm studies indicates that CSOPT adsorbent follows PSO model and exhibit a multilayer stepwise isotherm. CSOPT has high adsorption capacity of 1000 mg over gram. As for recommendation, investigate the influence of additional parameters such as temperature on the adsorption efficiency of CSOPT would provide a comprehensive understanding on the material's performance under various conditions and aid in optimizing the operational parameter. Other than that, conduct in-depth mechanistic studies to elucidate the specific interaction between CSOPT and Mg molecule by employing advanced analytical techniques. Lastly, extend the application of CSOPT to real wastewater sample containing Mg and other coexisting pollutants to evaluate its performance under more complex matrices to assess its practical applicability in real-world scenarios. This is some of the references used in this study. Thank you.